يفرشاقة بس ببرقة يفرشاقة بس ببرقة زي جمساي نار وراقة هي هي لا 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 يا فكر وراك كعفر لقاشي هيجي باي فكرك تقدر يرضعشي.
Hello students and online teacher. Welcome to physics lesson. I am Robot Demisahue. Today we start a new topic. Force and Newton's laws of motion. Introduction to dynamics, Newton's laws of motion. Motion draws our attention. Motion itself can be beautiful, causing us to marvel at the forces needed to achieve spectacular motion, such as that of a dolphin jumping out of the water, or a pole vaulter, or the flight of a bird, or the orbit of a satellite. The study of motion is kinematics, but kinematics only describes the way objects move, their velocity and their acceleration. Dynamics considers the forces that affect the motion of moving objects and systems. Newton's laws of motion are the foundation of dynamics. These laws provide an example of the breadth and simplicity of principles under which nature functions. They are also universal laws in that they apply to similar situations on Earth as well as in space. Isaac Newton's 1642–1727 laws of motion were just one part of the monumental work that has made him legendary. The development of Newton's laws marks the transition from the Renaissance into the modern era. This transition was characterized by a revolutionary change in the way people thought about the physical universe. For many centuries, natural philosophers had debated the nature of the universe based largely on certain rules of logic, with great weight given to the thoughts of earlier classical philosophers such as Aristotle, 384–322 BC. Among the many great thinkers who contributed to this change were Newton and Galileo. Galileo was instrumental in establishing observation as the absolute determinant of truth, rather than logical argument. Galileo's use of the telescope was his most notable achievement in demonstrating the importance of observation. He discovered moons orbiting Jupiter and made other observations that were inconsistent with certain ancient ideas and religious dogma. For this reason, and because of the manner in which he dealt with those in authority, Galileo was tried by the Inquisition and punished. He spent the final years of his life under a form of house arrest. Because others before Galileo had also made discoveries by observing the nature of the universe, and because repeated observations verified those of Galileo, his work could not be suppressed or denied. After his death, his work was verified by others, and his ideas were eventually accepted by the church and scientific communities. Development of force concept. Dynamics is the study of the forces that cause objects and systems to move. To understand this, we need a working definition of force. Our intuitive definition of force, that is, a push or a pull, is a good place to start. We know that a push or pull has both magnitude and direction, therefore, it is a vector quantity, and can vary considerably in each regard. For example, a cannon exerts a strong force on a cannonball that is launched into the air. In contrast, Earth exerts only a tiny downward pull on a flea. Our everyday experiences also give us a good idea of how multiple forces add. If two people push in different directions on a third person, as illustrated in the simulation, we might expect the total force to be in the direction shown. Since force is a vector, it adds just like other vectors. Forces, like other vectors, are represented by arrows and can be added using the familiar head-to-tail method or by trigonometric methods. These ideas were developed in two-dimensional kinematics. External forces are any outside forces that act on a body. A free body diagram is a drawing of all external forces acting on a body. Let us see. Newton's first law of motion, inertia. A body at rest remains at rest, or, if in motion, remains in motion at a constant velocity unless acted on by a net external force. Note the repeated use of the verb, remains. We can think of this law as preserving the status quo of motion. Rather than contradicting our experience, Newton's first law of motion states that there must be a cause, which is a net external force, for there to be any change in velocity, either a change in magnitude or direction. We will define net external force in the next section. An object sliding across a table or floor slows down due to the net force of friction acting on the object. If friction disappeared, would the object still slow down? The idea of cause and effect is crucial in accurately describing what happens in various situations. For example, consider what happens to an object sliding along a rough horizontal surface. The object quickly grinds to a halt. If we spray the surface with talcum powder to make the surface smoother, the object slides farther. If we make the surface even smoother by rubbing lubricating oil on it, the object slides farther yet. Extrapolating to a frictionless surface, we can imagine the object sliding in a straight line indefinitely. Friction is thus the cause of the slowing, consistent with Newton's first law. The object would not slow down at all if friction were completely eliminated. Consider an air hockey table. When the air is turned off, the puck slides only a short distance before friction slows it to a stop. However, when the air is turned on, it creates a nearly frictionless surface, and the puck glides long distances without slowing down. Additionally, if we know enough about the friction, we can accurately predict how quickly the object will slow down. Friction is an external force. Newton's first law is completely general and can be applied to anything from an object sliding on a table to a satellite in orbit to blood pumped from the heart. Experiments have thoroughly verified that any change in velocity, speed or direction must be caused by an external force. The idea of generally applicable or universal laws is important not only here. It is a basic feature of all laws of physics. Identifying these laws is like recognizing patterns in nature from which further patterns can be discovered. The genius of Galileo, who first developed the idea for the first law, and Newton, who clarified it, was to ask the fundamental question, what is the cause? Thinking in terms of cause and effect is a worldview fundamentally different from the typical ancient Greek approach when questions such as, why does a tiger have stripes? Would have been answered in Aristotelian fashion, that is the nature of the beast. True perhaps, but not a useful insight. The property of a body to remain at rest or to remain in motion with constant velocity is called inertia. Newton's first law is often called the law of inertia. As we know from experience, some objects have more inertia than others. It is obviously more difficult to change the motion of a large boulder than that of a basketball, for example. The inertia of an object is measured by its mass. Roughly speaking, mass is a measure of the amount of stuff, or matter, in something. The quantity or amount of matter in an object is determined by the numbers of atoms and molecules of various types it contains. Unlike weight, mass does not vary with location. The mass of an object is the same on Earth, in orbit, or on the surface of the Moon. In practice, it is very difficult to count and identify all of the atoms and molecules in an object, so masses are not often determined in this manner. Operationally, the masses of objects are determined by comparison with the standard kilogram. Look at the following simulations. According to Newton's first law, an object in motion continues in motion with the same speed and in the same direction unless acted upon by an unbalanced force. It is the natural tendency of objects to keep on doing what they are doing. All objects resist changes in their state of motion. In the absence of an unbalanced force, an object in motion will maintain its state of motion. This is often called the law of inertia. The law of inertia is most commonly experienced when riding in cars and trucks. In fact, the tendency of moving objects to continue in motion is a common cause of a variety of transportation accidents, of both small and large magnitudes. Consider for instance a ladder strapped to the top of a painting truck. As the truck moves down the road, the ladder moves with it. Being strapped tightly to the truck, the ladder shares the same state of motion as the truck. As the truck accelerates, the ladder accelerates with it. As the truck decelerates, the ladder decelerates with it. And as the truck maintains a constant speed, the ladder maintains a constant speed as well. But what would happen if the ladder was negligently strapped to the truck in such a way that it was free to slide along the top of the truck? Or what would happen if the straps deteriorated over time and ultimately broke, thus allowing the ladder to slide along the top of the truck? Supposing either one of these scenarios were to occur, the ladder may no longer share the same state of motion as the truck. With the strap present, the forces exerted upon the car are also exerted upon the ladder. The ladder undergoes the same accelerated and decelerated motion that the truck experiences. Yet, once the strap is no longer present, the ladder is more likely to maintain its state of motion. If the truck were to abruptly stop and the straps were no longer functioning, then the ladder in motion would continue in motion. Assuming a negligible amount of friction between the truck and the ladder would slide off the top of the truck and be hurled into the air. Once it leaves the roof of the truck, it becomes a projectile and continues in projectile-like motion. Look at the second simulation. According to Newton's first law, an object in motion continues in motion with the same speed and in the same direction unless acted upon by an unbalanced force. It is the natural tendency of objects to keep on doing what they're doing. All objects resist changes in their state of motion. In the absence of an unbalanced force, an object in motion will maintain its state of motion. This is often called the law of inertia. The law of inertia is most commonly experienced when riding in cars and trucks. In fact, the tendency of moving objects to continue in motion is a common cause of a variety of transportation injuries, of both small and large magnitudes. Consider for instance the unfortunate collision of a car with a wall. Upon contact with the wall, an unbalanced force acts upon the car to abruptly decelerate it to rest. Any passengers in the car will also be decelerated to rest if they are strapped to the car by seat belts. Being strapped tightly to the car, the passengers share the same state of motion as the car. As the car accelerates, the passengers accelerate with it. As the car decelerates, the passengers decelerate with it. And as the car maintains a constant speed, the passengers maintain a constant speed as well. But what would happen if the passengers were not wearing the seat belt? What motion would the passengers undergo if they failed to use their seat belts and the car were brought to a sudden and abrupt halt by a collision with a wall? Were this scenario to occur, the passengers would no longer share the same state of motion as the car. The use of the seat belt assures that the forces necessary for accelerated and decelerated motion exist. Yet, if the seat belt is not used, the passengers are more likely to maintain its state of motion. The animation below depicts this scenario. If the car were to abruptly stop and the seat belts were not being worn, then the passengers in motion would continue in motion. Assuming a negligible amount of friction between the passengers and the seats, the passengers would likely be propelled from the car and be hurled into the air. Once they leave the car, the passengers becomes projectiles and continue in projectile-like motion. Now perhaps you will be convinced of the need to wear your seat belt. Remember, it's the law of inertia. Today we start a new topic. That is all we have for today. Please the online teacher show Newton's second and third law. Thank you students, thank you online teacher. See you in another lesson. Goodbye.